In section 2.2, we're going to be verifying solutions of differential equations. Let's say we're asked to verify that this equation, y equals 4 cos 2x plus 6 sine 2x, is a solution to y double prime plus 4y equals 0. Well, note, we have y double prime here, so the first thing I'm going to do is take the second derivative of my function. So the derivative of 4 cos 2x, well, 4 is a constant. Derivative of cos is negative sine 2x times the derivative inside, which is 2. And the derivative of sine 2x is cos 2x times the derivative of 2x, which is 2. So y prime, if I simplify this first term, is negative 8 sine 2x plus 12 cos 2x when we simplify the second term. The second derivative is going to be negative 8 as a constant, and the derivative of sine 2x is cos 2x times 2, so I'm going to write it as 2 cos 2x. And the derivative of cos 2x is sine 2x times the derivative of 2x, which is 2, so it's going to be negative 2 sine 2x. And if you simplify this, you get negative 16 cos 2x minus 24 sine 2x. Now, all we're going to do is we're going to substitute y double prime in for here and y in for here and see if it makes the differential equation equal 0. So negative 16 cos 2x minus 24 sine 2x plus 4 times 4 cos 2x plus 6 sine 2x does this equal 0. When I distribute, 4 times 4 is going to give me 16 cos 2x and 24 sine 2x. So yes, indeed, the negative 16 and the 16 cancel, negative 24 cancels, so I do get 0 equals 0. So we have verified that y is a solution to that differential equation. Okay, a little bit of practice here. Let's determine whether the given function is a solution of the differential equation f double prime x minus f of x equals 0. Well, again, let's start with a. So I have to take the first derivative, which is going to be positive sine x, and the second derivative is cos x. Well, let's see, cos x, which is f double prime minus the original function. That does not equal 0, so this one's not true. For b, I have f prime of x is going to be negative 2 e to the negative x, and f double prime is going to be positive 2 e to the negative x. So f double prime is 2 e to the negative x minus the original function. And this does equal 0, so yes, this is true. And looking at part C, the derivative of k e to the x, well, f prime is just going to be k e to the x. F double prime will also be just k e to the x, so the second derivative minus the original function. Whoops, that should be an x, not a k up here. This does equal 0, so yes, this guy here is also a solution to the differential equation. All right, this is an actual multiple choice question from a practice exam, and it says the equation y equals 2 e to the 6x minus 5 is a particular solution to which of the following differential equations? Well, again, first thing I'm going to do is find the first derivative. And the first derivative of y equals 2 e to the 6x minus 5 is going to be 12 e to the 6x. And the second derivative is going to be 72 e to the 6x. And now I'm just going to go plug and chug. Let's start with a. Let's put the first derivative in. subtract 6 times the function, and let's see if this equals 0. So yes, 0 equals 0, and we found that our first answer is A. If A didn't work, then you try the second, third, fourth. That's probably your best strategy to attack those types of problems. So a solution of a differential equation can be checked by substituting the function and its derivatives into the original differential equation. So let's take a look at this next example, and it says a particle moves along the x-axis with its position at time t, given by the function xt equals e to the negative t sine t. Okay, in part A, they want us to find the time at which the particle is furthest to the left. Justify your answer. All right, we got lots going on here. We have a closed interval, 0 to 2 pi, and we're given the position is x, or e to the negative t times sine t, and we want to find when the particle is furthest left. So the first thing I have to do is figure out when the velocity is 0. So the first thing I have to do for part A is find the velocity, and the velocity is going to be the derivative of the position function. So it's going to be the first function times the derivative of the second, plus the second function times the derivative of the first. And this is really the same as x prime of t. If I set the velocity factor out in e to the negative t, I'm going to be left with cos t minus sine t. And now we have to figure out where the velocity is equal to 0. So it's going to be where e to the negative t times cos t minus sine t equals 0. Well, this guy is never 0, so we have to figure out when does cos t minus sine t equals 0, and that's going to be where cos t equals sine t in the interval 0 to 2 pi. Well, cos are equal in both quadrant 1 and quadrant 2, and that's when the reference angle is pi by 4. So at pi by 4 and at 5 pi by 4 are going to be the two times where the velocity is 0. So if we have our number line test from 0, there's pi by 4, there is 5 pi by 4, and in this first interval, if I do a sign check, we'll use, if we want to use pi by 6, and we did it at sign check, we stuck pi by 6 in here because pi by 6 is in the interval 0 to pi by 4. It'll work out that cos t minus sine t is positive. If I take pi, a number in between here, and plug it into cos t minus sine t, it's going to be negative. And a number out here like 7 pi by 4, and plug it into cos t minus sine t, it's going to be positive. So therefore, the particle is furthest left at t equals 5 pi over 4. All right, part B now wants us to find the value of A such that x of t satisfies and is a solution to this differential equation, again, over the interval 2 to pi. So notice I have x prime of t in here, x of t, I need x double prime t. So the first thing I'm going to do is find the second derivative. Again, remember our velocity was the first derivative, x prime of t. So here's my first derivative right here. So the second derivative, I have to use the product rule with this guy here. So it's going to be the first function. Whoops. So the first function is e to the negative t times the derivative of the second, which is going to be negative sine t minus cos t, plus second function, which is cos t minus sine t, times the derivative of the first, which is negative e to the negative t. And now if I factor in e to the negative t out, I'll be left with negative sine t minus cos t. And taking an e to the negative t out, this negative here will have to be distributed to those two guys. So that becomes negative cos t plus sine t. And now the sine t's will cancel. So my second derivative, I'm going to have negative 2 cos t's times e to the negative t will be negative 2 e to the negative t cos t. So now I'm going to plug in back into my equation here, a times the second derivative plus the first derivative plus the original function. Therefore, I'm going to get a times the second derivative plus the first derivative, which is e to the negative t cos t minus sine t, plus the original function, and that all equals 0. That's supposed to be a sine t there. Okay? So now if I multiply these together, I get negative 2a e to the negative t cos t. If I distribute the e to the negative t here, I'm going to get plus e to the negative t cos t minus e to the negative t sine t plus e to the negative t sine t. And this all equals 0. Well, these two guys are going to cancel out. So now I'm left with two terms equaling 0. So I'm going to factor out my common factor, which is e to the negative t cos t. And if I do that, I'll be left with negative 2a plus 1, and this all equals 0. So therefore, either this is 0 or this is 0. And since we're just solving for a, I'm just going to set my second term to 0. And if I solve for a, I'm going to get a being 1/2. So there would be your answer to that particular question. All right, the last question is dealing with, it's on the 2015 free response section. And we're just going to deal with part D right now, because that's all we can do really on this one. And it says find the values of the constant m and b for which y equals mx plus b is a solution to the differential equation. So we know that y equals mx plus b is a solution to the differential equation, which was given in the part A or earlier in the question as dy dx is equal to 2x minus y. Well, if I take the derivative of this, I get dy dx is equal to m because b is a constant. So therefore, I can say dy dx over here is m is equal to 2x minus y, and y is the original question, or sorry, the original solution, which is mx plus b. And if I distribute, I get minus mx minus b. And if I bring or factor in x out of these two terms, I'm left with x times 2 minus m minus b. And notice, since there are no x's on the left-hand side of my equation, this part here must be 0. So 2 minus m has to equal 0. So therefore, m is 2. And therefore, looking at the other part of this equation, m must equal negative b. So therefore, b must be equal to negative 2. All right, so that question, or that a lesson there, we had a couple of AP free response questions worked in at the end where this concept does come into play the odd time. And your assignment is a handout. So there's your handout that you received in class. So give those a try. If you have any questions, you see the answers are on the bottom there. We can discuss them in class.